Hey guys, this is Mr. Sal. We're going to look at OR inequalities. So we've already been solving inequalities in general, and we're still going to be using the same rules, but OR inequalities are compound inequalities, meaning that we're dealing generally with two at a time, and then using interval notation and graphing to express our answers, because as we've seen from 2.1 that there's an infinite number of answers for each of these, or at least there is generally. So before we get into it, let's just look at what a set is, okay? So a set is just a bunch of stuff. Math people call the stuff in the set elements or members sometimes. Stuff or elements are just not listed more than once in your set. And we've seen these with, these symbols represent real numbers, rational numbers, integers, whole numbers, and finally natural numbers. So they're all kind of subsets of each other for the most part, but they're also just basic sets of numbers. Something we want to remember with these is when making a set, generally we use fancy brackets like this. Now I think mine are pretty fancy, and then we close them with brackets like this. That one wasn't too good, but that's not the point here. Is on a test, I have to mark problems wrong if you don't use these to indicate a set. So the way to make these is to open them, and that would be the one on the left. All you're going to do is make an S, and then you're going to connect it with a 2. Now for me, that's, again, it's not super fancy, but it's still pretty fancy right there. To close it, you're just going to reverse those. You're going to make a 2, and then an S. And you got some fancy brackets right there. Now again, remember that line right there. If something's listed more than once, we do not list it a second or third or more time. Just list it once. So this is list or roster method right here. And now again, we're using those fancy brackets. And to start off, it's just listing these things: shoes, shirts, sandals, socks, smocks, and suspenders. In set notation, sometimes we don't list all of them, but we can define it a little bit differently. So again, we got those fancy brackets, but this would be said as X such that X is something you wear that starts with S, like a smock. So that could have been called, for example, set C, and then set C would be a set of things that you wear that start with S. Now it is possible to have an empty set, meaning that there's nothing in the set. In that case, we indicate it with the two fancy brackets but nothing between, and in some cases we'll use this symbol right here to indicate that it's a null set or empty set. To indicate that an element is part of a set, use the symbol, and that's just an element is part of. If we threw a slash through that thing, then it indicates that the element is not part of the set. So for example, 5 is an element of set G, would be the same as writing it like this. So if I had just written these three symbols right here, I would read it as 5 is an element of set G. Now if I wanted to say, because I don't want to write all this stuff right here, negative 10 is not an element of set W, I could just write, again, these three symbols. Negative 10 is not an element of set W. And it would mean the same thing. Alright, let A be these four numbers. This is a set A, 10, 20, 30, 40. Indicate if the statement is true or false. 15, and again, I'm just reading this the way it's shown. 15 is an element of set A. Well, I know that 15 is not in the set because it's not listed in the set A. Therefore, this would be a false statement. What about something like this? Set A is the letters ham and cheese, and set B is bacon LT. Well, E, I can't find it in set B, but I do see E in set A, so E is an element of set A. And that would be the answer for this one. Now in this lesson, we're not going to concern ourselves too much with the bottom there, the intersection, which is generally indicated with that word "and" right there. But again, the purpose of this lesson is to focus more on the union of sets. Now it's generally a comparison of two sets, but it is possible to compare more than one or two at a time. Now union is just, it's a new set, which is kind of indicated right here, right? This is set A and B. I'm sorry, A or B. And it's shown with this U right here for union. Now, it's any element that is in either set, meaning if it's part of one, it's part of the union. So, on this one, we see set A, and that means everything in A is part of the union, but also everything in B. But remember, we're not listing repeats more than once. So 1, 3, 4, 5 are good. They're all here in the set of the union. But then 7, which appears in both, we're only going to list once right there. Now if we go from least to highest, we would see 8 there, and then 9, and then 11 in the list. But again, 11 is not going to be listed more than once. And then finally we have 15, 19, and 20 as part of the union, because if it's part of one or the other or either set, then it's part of the union as well. Alright, so given set A is 32, 45, 47, 60, and set B is 31, 32, 34, 45, 47, 48, and 51, we'll find the following. Now again, we're not going to concern ourselves with the intersection just yet. So I'm just not going to worry about that one just yet. So let's look at A and the union with B. So once again, we need to start with some fancy brackets here. And we'll just fill in the blanks. So if we start again with the lowest one, I got 31. Next up is 32, which appears in both. Next up would be is 34. But then again, we see 45, which appears in both. But I will only list once. Same with 47, which appears in both. And then we got 48, which appears in set B. And then 51. And then finally 60 here at the end. So I see I've kind of marked off all the numbers, including the repeats, which I don't have to list more than once. And this would be the answer for that. Now keep in mind, if for some reason you're going to list these more than once on a test, then I do have to mark it wrong. So as we move forward, looking more in these inequalities, like these two, just remember that a solution only needs to be part of one or the other in order for the whole thing to be true, right? So just by looking at these ones, even, we got x is less than 5, but also x is greater than or equal to 12. So if we looked at a list of numbers, right, like negative 100, well, negative 100 is less than 5, so even though it's not greater than or equal to 12, because it is less than 5, this would still make this statement true, or the number is part of a solution set for these two inequalities. On the other hand, if we took a number like 0 even, it would still be in the case like negative 100 is. It's less than 5, even though it's not greater than or equal to 12, because it is less than 5, it is a true statement. Well, what if we took a number like 8? Well, 8, it's not less than 5, and also it's not greater than or equal to 12. So 8, as it turns out, would not be a solution for this compound inequality. Now, remember, this is the nice thing about it. It only needs to make one or the other true. So if we start looking at a number such as 15, well, now it's going to make the x is greater than or equal to 12 true, but it would make the x is less than 5 false. But again, it's only got to be one or the other, so 15 would be a solution for this compound inequality. Now we need to think as well, in these inequalities, how many solutions are there? So even if we just looked at one of these two, x is less than 5, how many solutions are there for this single inequality? Well, the truth is, how many numbers are less than 5? And that's really what we're asking here. And the truth is that there are an infinite number of solutions that are less than 5. Now, demonstrating or communicating or writing that there's an infinite number of solutions can be a little taxing, which is why we do have interval notation, as it turns out. But in order to do interval notation, we generally use a graph which will visually show us what the interval is of values that would make the inequality true. So let's look at these separately. And generally there is some solving involved, just like we've done in, I think it was 2.1, where we were solving inequalities. These are already solved for us, meaning there's nothing else we need to do for simplifying these. So what we really need here is a line, and the two values we're looking for would be 5 and 12, because that's where we find that x would be equal to those values. So we'll look at 5 and 12, okay? Now everything that we learned in 2.1 should be coming back. For example, let's focus first on x is less than 5 here, okay? So it's not equal to, so at 5 we'll have an open circle there. And the inequality is not eating the x. Therefore, this line would go to the left. On the other hand, though, we've got x is greater than or equal to 12. So at 12, I'd have a circle that is closed because it is equal to, which means 12 would make a true statement for this compound inequality. And then also, it's eating the x, so it goes to the right. So we can see all the values to the left of 5 on this number line would make a true statement for this compound inequality. And also 12 and anything to the right on the number line would also make this a true statement. So we need to show this using an interval notation. So we've already seen interval notation. We know as far to the left as this thing goes would be negative infinity. And then I just kind of move to the right, and this purple line, it stops at 5, which is not included. So we have just a parenthesis right there. And we will unite this with the other line, which starts at 12, which is included, so I have a bracket there. And then how far to the right does this thing go? Infinity. And infinity and negative infinity are never included in the solution set, so we have just the parentheses there for those. So this would be the interval, and we've already seen some intervals, right? So this is just kind of like having two intervals to demonstrate the one, a compound inequality. But again, we need the two intervals because on the number line we have the two lines going in opposite directions there in purple and red. So let's try this with another example here. So we will solve these, and then we'll graph them and give the interval notation on these also. Now, one thing to do, or one thing to remember when we're solving these inequalities, just like we did in 2.1, is if we ever need to divide both sides of the equation, or multiply both sides of the inequality rather, by a negative, then it flips the inequality. While we won't see that on either of these, we will see it eventually on some of these other examples. So we're going to proceed with this one on the left here. 6x plus 3 is less than negative 15, and solve it for x. So after showing all the work there, and you can check it, x appears to be less than negative 3. So anything less than negative 3 would make that one inequality true. Now we'll do this one on the right here. 5x minus 7 is greater than or equal to 13. So this is the inequality that we get from solving this one after dividing by 5 on both sides. Now don't forget, for our inequality, it is an OR statement which we do need to include as part of the solution in terms of the inequality. Next up, let's go ahead and graph these two. Now for this number line, I'm including 0 in the middle there, just so we know that it is between the two. And at -3, we would have an open circle, because -3 is not included, doesn't have the equal part there with the inequality. And this one is not eating x, so the line goes to the left. Now the purple one, x is greater than or equal to 4, so this one is equal to 4, so I can fill this in here, right? And it's eating the x, so it goes to the right. And that would be the graph. Finally, we want the interval. So this red line goes as far to the left as -infinity. It stops at -3. And then we're going to unite this, and we're uniting it with the purple line. Starting at 4, which is included, so we have a square bracket there. And this one would go all the way to infinity, which also is not included. So overall, we have this solution here, and it's come in 3 parts. We have the inequality with the OR statement, and we have the graph and the interval. Alright, in this example, I am going to have to flip one of the inequalities because I'm going to end up dividing both sides of the inequality by a negative. So I'm going to show the work for that. And I'm going to start with the left one. -5x minus 2 is greater than or equal to 23. So just after performing the first principle of equality, I've got -5x is greater than or equal to 25. But at this point, I need to divide both sides by -5. And since I'm dividing both sides by negative, it will flip the inequality. So I end up with x is less than or equal to -5. Alright, this inequality on the right, 4 times the difference between x and 4 is less than -8. And after showing the work there, I get x is less than 2. Now I'm going to put my OR statement there because I tend to forget to with these inequalities. And I'm going to move into the graph, even though eventually we're going to have to change that inequality, and I'll show you why. Alright, so at -5, that's an equal part to it, the inequality, so I know it's a closed circle. It's not eating the x, so it goes to the left. Next up, in purple there, I've got x is less than 2, so that's an open circle at 2. This one also is not eating the x, so it goes to the left as well. Well, this is an OR statement, right? So when I look at the interval for this inequality, I know that it's going to go as far to the left as we can, which is -infinity. But if I said, well, I'm going to stop at 5, that's not necessarily stopping at 5, because as soon as I follow this line to 5, I can jump on the purple one and follow it to 2. So it doesn't actually stop at 5, because it continues on to 2, which is also not included. So we end up with this interval, and rewriting the inequality would show that, as it turns out, x is just less than 2. So we actually didn't need this inequality right here. Now I'm crossing it out. I would still show the work for that on a test, but ultimately the real answer for these 3 would look something like this. Now on a test for me, I'm okay with showing this point right here because it's still consumed by that purple line right there. Alright, this one doesn't ask for the interval notation, but I'm still going to show it because I think it'd be good to see it. Now for both of these, there's 4 different ways to start them, but after you start, there's generally just one path to follow after that. So I'm going to show the work for these, and after the division here at the end, I get x. I put equals there, didn't I? But I meant to put, of course, greater than. And I didn't divide both sides by a negative. Even though this is a -12, I divided it by a positive, so it's not going to flip that inequality. So I get x is greater than -2. Alright, I'm going to solve this second inequality pretty much the same way. Alright, so this is the inequality I get from solving the right side there. And again, I'm going to put my OR statement just in case we need it. Now, whether you did it the same way that I did with the following or the starting step on these, you may have gotten these 2 inequalities, which would also still be true again, it kind of depends on which side you put the x's on. So you may have had negative 2 is less than x, or x is less than negative 3. And again, it doesn't matter which one you choose, because they're still communicating the same thing. So these are the two values that we have. And I'll start with x is greater than negative 2, so it's an open circle because it's not equal, and it's eating the x, so it goes to the right. The purple one, still an open circle because it's not equal, but this one's not eating the x, so it goes to the left. So notice whether we do the ones in red or purple or the green ones, we end up with the same graph because we're considering is the inequality eating the x's. And in one case it is, in one case it's not, so they're going in opposite directions. And as I promised, this is the interval. Of course, it goes all the way to negative infinity. It's stopping at negative 3. And we'll unite this starting at negative 2, which is not included. And this goes to infinity. So it didn't ask for the interval, but there it is anyways. And yes, we do need this or statement up here as part of the inequality part of the solution. All right, so this example, we wanted to really emphasize what the or statement is saying to us. And we're going to see something interesting happen when we graph these two. So let's go ahead and get started just by solving them. So just here on the left, I get x is less than 4, showing all the work there with the distribution to start off with. Now this one on the right. And so here on the right in purple, I've got x is greater than 1. Now again, this is an or statement, so I'm going to write it in right now, even though eventually we may not need it. So let's go ahead and move on to the graph for this one. So we're comparing the values of 4 and 1, and we'll start with 4. At 4 I've got an open circle, and this one is not eating the x, so it's going to the left. Or x is greater than 1, so at 1 I've got an open circle. This one is eating the x, so it will go to the right. So what do we notice about this one? Well, we should notice that the line, the red one specifically, is going all the way to negative infinity. Now again, if we consider moving to the right, we wouldn't stop at negative 1, because that's the purple line. So I can write either the red or purple line over until I get to 4. And at this point, I'm going to have to hop on the purple line and then move all the way to the right. So it never actually stops. This one goes all the way to infinity to the right. So what does this mean for the inequality? It means that x is just going to be all real numbers. Now this is the symbol for all real numbers. Or you could, if you wanted to, write it out like this. So the final answer would be the graph here, the interval, and then also showing the inequality. Again, we're not focusing on this or statement right here anymore, because x is all real numbers now. Meaning it wouldn't matter what value of x, like if we went back to the two original inequalities, it wouldn't matter what value of x I put in here or in here. One of them will always be true no matter what x value or number I put in for x. Alright, this is our last example for this lesson. Solve graph and give interval notation for this inequalities. So just like I've done in the other examples, I'm not really going through the solution process or the use of the principles of equality, just because we should be used to those now. But I am showing the work so you can compare what you did with what I have up here. So I'm going to start with negative 6x plus 7 is greater than or equal to 25. And right here we see at that last step I've divided both sides by a negative 6, so I'm going to have to flip this inequality so that it's eating to the right, and that would be now negative 3. Alright, let's move on to the next one. So there we go, we got x is greater than 14 right there after applying the principles of equality. So again, I'm going to put my or statement just so I don't forget it. And then let's go ahead and prepare the graph. So maybe something like this. And at negative 3, again, this one is equal to, so I'm going to close in that circle. It's not eating the x, so it goes to the left. And at 14, I've got an open circle. This one is eating the x, so it goes to the right. So my interval goes all the way to negative infinity. it's going to stop at -3, and I would need to unite that with the purple one, which starts at 14, not included, and that goes to infinity, which is also not included. So we have the solution on this one, the graph, and the interval notation. Now before I end this video, I just want to reiterate again, what the graph is communicating is the same as the interval, which really stems from that inequality, meaning anything less than or equal to -3 would make this true because that would be part of the set. But anything anything greater than 14 would also would be a part of this solution set as well. So just like we did in the beginning, it's listing all the values, but it's impossible to list an infinite number of values. So we can show it with the graph, or even the inequalities, but also the interval. Alright, thanks for watching, you guys. I hope that really helped you guys out. I know a lot of people struggle with these inequalities, especially with these or statements and statements. So thanks for watching. If it did help you, please subscribe to the channel, like the video, and make a comment below.